All right, so say I was asked to simplify 2x minus 6 over x squared minus 8x plus 15, and I got the solution 2 over x minus 5, with the excluded values x, or restricted values x can't be 3 or 5. So there's 3 methods I can now do to model the problem and see if I can convince myself that this answer is correct. The first method is that we are going to evaluate the problem. So when we evaluate, we pick a number for x, and we just want to be careful that the number we pick for x is not one of the restricted values, because then we're going to get that when we plug it in, we're going to get that the answer is undefined, and that's not really going to help us to see what's going on. So I just picked 2. You could have really picked any number. I'm going to plug a 2 in everywhere I see an x and see what happens when I evaluate. So I grab my calculator, I plug everything in, and get an answer of -2/3. So now what I'm going to do is plug that same number into my solution and see if it gives me out the same value. So I plug in a 2 for the x in my solution, and I get 2 over -3. Well, since a positive divided by a negative is a negative, both of these, and a negative divided by a positive is a negative, give me the same value of -2/3. So I know at least if x is 2, that these two expressions are equivalent to each other. It doesn't show me that they're equivalent all the time, but it does show me that they're equivalent when x is 2. The next method to show that these two expressions are equivalent is by graphing. So I've typed both of my expressions into 2 separate lines on Desmos, and they've both been graphed separately. And if I turn one off and turn the other one on, the blue and the red, I can see that these lay right on top of each other. So that means they have all of the same x and y values. So for example, if I plug in 8 to either function, I get out the same number, 0.667. If I plug in 6 into either function, I get the same answer of 2. So just like evaluating, this shows me a whole bunch of x's that I plugged in and a whole bunch of numbers I got out. And it shows me that all the ones I can see are the same. So instead of having one x value I know works, I now know all of the x values I can see at least are the same. Finally, the last method is your justifying algebraically. So it's using the properties of algebra to prove that step-by-step it worked. So the first problem with evaluate is sometimes there might be some x values that you plug in that won't work, even though the choice, the one that you did pick, happened to work that time. The problem with graphing is every once in a while, the graph might match in the part that you see, but it's not necessarily going to match all the time. Justifying algebraically is following the rules of mathematics, the laws of algebra, so it's always going to prove that it works all the time. So the first thing I'm going to do here is I'm going to factor both the numerator and the denominator. So factoring is actually using the distributive property, right? You're undistributing your 2 numbers. So it's following, again, a step of algebra because you are, like I said, using the distributive property. We can just say here that we are factoring. Once we've factored, we can see here, hopefully already, that we have made a giant 1. Now, in practice, when we're solving these problems, you probably just cross it out and make a 1. But since we're trying to do a nice algebraic justification, I'm going to rewrite this as 2 over x minus 5 times x minus 3 over x minus 3. And why can I break that up? Because when I am multiplying fractions, I multiply numerator times numerator, denominator times denominator. So this is the algorithm for multiplying fractions. It tells you that you can just split up the numerator and denominator because you can use the algorithm kind of in either direction. So it's kind of like we're using this algorithm backwards by breaking it up instead of pushing them together. All right. The next thing that we can do now is say that x minus 3 over x minus 3 is equal to 1. So 2 over x minus 5 now we have multiplied by 1. Okay, and then of course when you multiply by 1, you just get an answer of 2 over x minus 5. And that is the identity property of multiplication. I'm spelling that wrong. Identity property of multiplication. And that says that when you multiply a number by 1, you get that same original number. So because we have followed the steps of algebra, and the steps of algebra never fail us, we can see that this original expression here is equivalent to this final expression that we got as our answer.